Welcome to the Siemens FEA Phase 2 poster presentation. This project looks to build upon the work completed by the UNCC team during Phase 1 of this project. This project arose from the need to validate the stresses on the copper windings on a rotor of a utility-scale generator. The goal of this project is to collect strain data from the copper windings and compare the data with an FEA model that's been developed by Siemens. The primary requirements of the design are that the system must remain secure when the rotor is operating at speeds of 4,300 rpm, and it must be able to withstand temperatures of up to 130 degrees Celsius. The figure at the center of our poster represents CAD models of our mounting board, which will hold most of the components except the strain gauges. The primary components of the board are the two slots for the two batteries, a chip for processing the data, and a place for a control strain gauge if we need it, and the clamp. Below the CAD model, an exploded view of the mounting board is provided, as well as a wiring diagram of the electronics that will be used in this project. Calculations were performed to determine the best material choice for the mounting board and to ensure it would be able to withstand the forces and temperatures of the rotor. The test plan for the instrumentation system and future plans of the overall project will be discussed later in detail.
The team consists of Matthew, Jay, Theodore, and Joseph. Dr. McAlpine is our faculty mentor, and Larry Zeller and Hynek Latang are our industry supporters. We were tasked with validating the instrumentation setup that was designed by the previous semester's team and using it to collect strain data on a rotor while it is undergoing a balancing operation. The strain data will be collected on the copper end windings of the rotor. The collected strain data will be used for comparison with data from Siemens' FEA model. The instrumentation setup must be able to resist the temperatures of the balancing operation, minimize signal noise, and stay attached at high rotational speeds. The design consists of a DAC that is mounted to a 3D printed mounting platform and is powered by two batteries, a USB receiver, and several strain gauges. The parts were chosen based on their ability to survive the high temperatures of the balancing operation. A 3D printed platform was chosen to minimize turnaround times if changes are needed. Ultim 9085 was chosen as the material for our mounting platform because of its temperature resistance and high compressive yield strength. Our testing plan requires us to install the strain gauges, wait 24 hours for the adhesive to cure, and then install the rest of the instrumentation. The rotor will then be placed in the balance bunker and data will be collected during the balancing operation. Following data collection, the entire instrumentation setup will be removed from the rotor. Our future plans include having our mounting platform 3D printed, creating an error compensation table for the strain data, analyzing the data we collect, comparing it to the strain data from Siemens' FEA model, and preparing for additional test runs.